Hi, welcome to Algebra 2 Common Core. In Lesson 7, we're going to learn about a type of function called a power function. Let's start by looking at polynomial functions that we are pretty much acquainted with. A polynomial function is a function that has the form y equals. Now, don't be put off by this notation here. You'll notice that each term has a coefficient. The coefficient is the a sub n. That just means it's the coefficient of the nth term, or the coefficient of the term that has the power of n. This just means the coefficient of the variable with the power of n minus 1. So you'll notice that our powers on our x's are just decreasing by 1 as we keep going down the polynomial. A polynomial, of course, means that there could be many terms in the function. Now, let's talk about some of these polynomial functions that we are very well acquainted with. The first one, with a degree of 1, would be of this form: y equals a times x plus b. So I've got a coefficient in front of my x to the first power, and then my b doesn't have a variable, so it's a constant term. We know this kind of function as a linear function. So you've been working with linear functions probably since 8th grade. A polynomial of degree 2 just means that my highest exponent is going to be a 2. So that kind of function would look like this: y equals a times x squared plus b times x plus c. Again, just like the polynomial function in the general form that I talked about in the top line, each term has an exponent on the x, and it has a coefficient. Now, the coefficients can either be positive or negative, and in the case of a, it cannot equal 0, so we know that we have a leading term of x squared. In the case of b or c, it is possible for them to be 0, in which case I would only have one term in my polynomial function. This kind of function, because its highest exponent is a 2, is of course called a quadratic function. And we've done a lot of work with quadratic functions in this class already. Now we're going to focus in this unit on what we call higher degree or higher order polynomial functions. So far we know quite a bit about linear functions and quite a bit about quadratic functions, but our focus is going to be on polynomial functions with higher exponents. So we're going to start with the simplest kind. This is going to be a simple type of polynomial called a power function. Let's start by defining a power function in the box in your notes. A power function has the form y equals a times x to the b. So notice the parts of this power function. The a is just going to be the coefficient, x is our variable, and b is going to be the exponent on the x. You'll notice that right now we're only talking about terms that have an exponent that are positive. So 1 or 2. We want to go up to higher powers, so we're going to be talking about x to the 5th, x to the 6th, and see how our power functions look. Let's in this box jot down a few examples of power functions. So one example of a power function would be y equals 2x to the 6th power. We could also write this in function notation, so I could say f of x is equal to, how about negative 5x to the 4th power? Or I could look at something like, how about g of x being equal to 4x to the 10th power. So we see that we have a lot of different powers that we can use in our power function as long as our power is a number that is bigger than 0. In example number 1, we're going to take quite a bit of time in our notes today to sketch the functions that are the basic power functions. So you see that I've got 5 power functions that are listed here. F of x equals x, g of x equals x squared, h of x equals x cubed, j of x equals x to the 4th, and k of x equals x to the 5th. If you'd like to, you can use your calculator for this part of it so that we can create a table of values for each of these power functions. Now, of course, our very easiest power function is just f of x is equal to x. So that tells me that the output is equal to the input. So for this first table of values, I'm going to have when the input is -3, output also -3. Input is -2, output would be -2, and so on. So I'm going to get a -1, a 0, a 1, a 2, and a 3. I think we can all picture what this is going to look like. On our graph, this is going to be the line where the x and the y coordinate match. So it's going to be our diagonal line that looks like this. So this is my function, f of x is equal to x. And this shouldn't be a surprise to us. We've seen this kind of function over and over again. I'd like you to pause the video for a minute and please fill out the table of values for g of x equals x squared. After you make the table of values, then go ahead and sketch the curve. And when we come back, we'll talk about the function h of x equals x to the 3rd power together. So looking at g of x equals x squared, I notice a pattern that we've of course seen before. This is our quadratic function. So I see that I get as my graph the parabola shown there. So that's going to be the graph of g of x is equal to x squared. Now as we create these graphs in these table of values, please start thinking about the inputs versus the outputs and how our graphs might be similar and how they might be different. Let's go ahead and do h of x is equal to x cubed. I'm cubing each of these inputs, so -3 cubed is -27. -2 cubed is -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. Now pause the video for a minute and sketch out this graph. It's not necessary to make little notches on my axes, as long as we get a sketch of what the shape of this graph would look like and where it would cross my x and y axis. So looking at the sketch of my graph, I see that I have the function h of x is equal to x cubed. Do you notice how the left side of this graph goes down indefinitely into the negative values, and the right side of this graph goes up indefinitely into the positive values? That, of course, corresponds with my table of values. Now pause the video for a minute and do the same thing with j of x equals x to the 4th. Fill out your table of values and sketch what the shape of the graph would look like based on those values. Compare your table of values with mine for j of x, and you should see a very familiar shape to this graph. It looks very similar to g of x, which was x squared. Do you notice some similarities in our inputs and outputs? Do you see how some of the values repeat in the table? So this will be very interesting for us to analyze as we go through this unit. You'll notice, though, that a little bit of a difference is that g of x equals x squared doesn't get as big as quickly as j of x equals x to the 4th does. Now let's go ahead and do x to the 5th as well. So -3 to the 5th power is -243. -2 to the 5th power is -32. -1 to the 5th is -1. 0 to the 5th is 0. 1 to the 5th is 1. 2 to the 5th is 32. And 3 to the 5th is 243. I hope you're thinking about, as we find each output for the corresponding inputs, are you thinking about whether these functions are even or odd? So think back to our definition of what an even function is and what an odd function is, and be able to compare which ones are even and which ones are odd. When I go ahead and graph these, this graph, k of x equals x to the fifth, I notice that this graph also has a shape that we are familiar with, that we've kind of seen before. Again, noticing though that my values get very big very quickly on the right end and very small very quickly on the left end. So this is the graph of k of x is equal to x to the fifth power. Now, as I said before, let's talk about whether each of these functions are even functions or odd functions. So in the case of f of x is equal to x, when I look at the first input and the last input, I notice that as I'm changing my input to the opposite, I also get the opposite output. So if I have opposite inputs giving me opposite outputs, I know, of course, that this function, f of x, must be an odd function. So going back to our definition of even or odd. Now for g of x, we've already talked about a parabola graph, and we notice, again on the table of values, that when we have opposite inputs, the outputs don't change. The outputs are actually the same outputs. I can see that, of course, by looking at a comparison between, for example, an input of -2 gave me an output of 4, but an input of 2 also gave me an output of 4. This is just our definition of an even function. So going along the line here, h of x, I notice that opposite inputs give me opposite outputs. So that must mean that this function is an odd function. For d, I see that opposite inputs give me the same output, so this one must be even. You're starting to notice a pattern here. And for the last one, k of x is equal to x to the fifth, when I look at the table of values, I also see that opposite inputs are producing opposite outputs. So this function is also odd. So pulling this all together, I think that we see that our even functions are the functions g of x is equal to x squared, and j of x is equal to x to the fourth. On the other hand, the odd functions would be f of x is equal to x, h of x is equal to x cubed, and k of x is equal to x to the fifth. Now, of course, when we think about this, that is going to make sense given what our exponents are in each of those power functions. So looking at exercise number 2, it says which of the following power functions is shown in the graph below. Explain your choice. Do without the use of your calculator. So did you notice in our last graph, all of those 5 graphs that we did, that when we had odd functions, that was shown on the graph as the graph going from the bottom left-hand corner to the upper right-hand corner. So the smaller inputs produced very big negative outputs, and the bigger inputs produce very large positive outputs. The even functions, however, when we looked at the graph, both ends of the graph went in the same direction. So that's going to be something that's really important for us in this unit. I see that for the graph in exercise number 2, both of the ends are going in the same direction. So same direction is going to tell me that this must be a power function that has an even exponent. It is an even function also because it's symmetric with respect to the y-axis. So that tells me that automatically I'm going to eliminate choice number 4 because that has an odd exponent, and choice number 1 because that also has an odd exponent. But now we have two choices for our function. Is it 6x to the 8th or is it negative 3x to the 10th? Well, I think you're right if you think that it's number 2, because I see that unlike our parabola and our 4th degree function above, both endpoints go below the x-axis, So if they both go below the x-axis, what that tells me is that I had a negative coefficient. So that negative 3 out in front told me that the graph was reflected over the x-axis. And that's what makes the graph open down instead of up. So all of these pieces come together to tell us what kind of power function we have. I want to introduce some notation that's going to be really important for the second half of this unit. This notation is going to help us describe what we call the end behavior of a function. So the end behavior just tells me what's happening on the ends of the function as x is getting really big and as x is getting really small. Well, we have a notation to tell us which way we're going. X arrow infinity just means as the x values, and of course we know our x values to be the inputs, are getting very large. If I've got the notation x arrow negative infinity, that means as the x values are getting very small. Now, very small, another way to think of that is a very big negative number. So as I'm going to the left side of my graph, as my x value is approaching negative infinity. Now look above to example number 2. I want to add one more piece of notation about this end behavior. So I could describe the end behavior for example number 2 as saying, when x is getting very large, when x is approaching infinity, what's happening to the y values? The y values are going down, so they're getting very, very small, so the y values are approaching negative infinity. Likewise, when x is approaching negative infinity, so that means on my graph I'm talking about this side of my graph, the left-hand end of the graph. When x is approaching negative infinity, y is also approaching negative infinity because again I see that my graph is heading toward the lower half of the y values. They're getting very, very small or very big in the negative direction. So it's going to be important for us to read notation like we've just read here. Lastly, in this lesson, we're going to take a look at a comparison in example number 3 between two functions. I want you to stop the video and enter these functions into your graphing calculator. It's going to be very important that you put these into your calculator so that you see what's going on with the graphs. If you've got a color graphing calculator, all the better, so that you can compare the two graphs on one set of axes. I'm going to do the two graphs on two separate axes in our notes, so I want you to do that as well. So in y1, please enter the first function, y1 equals x cubed minus 2x squared minus 29x plus 30. And in y2, please enter the function just y2 equals x to the third. We're going to make comparisons between these two functions as we change the window on our graphing calculator. So pause the video and enter those first of all in y1 and y2, and then come back so that we can talk about the window. Now, for my first window, for the set of graphs that we're going to do of y1 and y2, I want your x values, so hit the window key, and make your x min be negative 10, your x max be positive 10. That's usually what we have. And we're going to count by ones. Now we do have to change our y's to our normal settings. I want my y min to be negative 100. I want my y max to be positive 100. And it would make sense to count by tens, although it's not going to be that important for us when we put this on our axes to sketch. So adjust your windows, hit graph, and I want to sketch these two graphs on this axis. Now it's actually not that important for you to look at your table of values for this. Instead, just hit graph now that we've adjusted the windows, and let's sketch the graphs that we end up with. So my y1 graph looks like a graph, so I'm going to do y1 in blue and I'm going to do y2 in red so that it matches your graphing calculator. For y1, I see that my graph is going to look something like this. I'm going up quite a bit, coming back down, crossing the y-axis, crossing the x-axis 2 more times, and this is my graph of y1. Now, when I look at the graph of y2 in the very same window, this graph looks something like this. And we saw that on our previous page of notes. So this is my graph of y2, which is just the x cubed function. So I can look at these and say there are some similarities, but clearly there's some differences as well. Now in part B, we're going to keep our functions the same, so don't switch your y1 and y2. What we want to switch this time is our window. So make your x values go from negative 20 to 20. You might want to count by 2's this time instead of 1's. Now look at how big we're making our y's. I want my y min to be negative 1,000, my y max to be 1,000, and how about if we count by 100 this time? So go ahead and make your graphs for both of these, so just hit the graph key. And you'll notice that my y1, while I know it's exactly the same y1 graph that I drew in part A, it looks different just because I've adjusted my window. So the graph now looks like this, increasing, coming up just by a little bit, goes down just a little bit, and my graph of y1 in this new window looks like this. Now if I switch over to my y2, you'll notice that my y2 graph looks very similar to what I had before. It looks like this. In the last set of axes here, I again want to adjust my window. So this time my x min is going to go from negative 100 to an x max of 100. How about if we count by tens? My y min is going to go from negative 100,000 to positive 100,000. So when I zoom out on these two graphs, notice that the graph of y1 starts to look a lot like what I've had previously for the graph of y2. That's my y1 function. My y2 function, oh so similar. So I hope that you're noticing here that as my window gets bigger and bigger and bigger, as I zoom out on these two graphs, what has happened is that my y1 graph and my y2 graph, when I've zoomed out so far, both look pretty much the same. So we can base our next conclusions on that information. What is really going on here is that this x cubed function and this function that has as its highest exponent y equals x cubed minus 2x squared minus 29x plus 30 behave very similarly when I'm looking at just the ends of the graphs, when I'm looking at a window really zoomed out. So that information is going to be really important to us. So in conclusion, we're talking about two different kinds of power functions in this section. Y equals a times x to an even power, versus y equals a times x to an odd power. When I've got an even power as my highest exponent on my power function, then I see that the tails at the end of my graph go in the same direction. Looking carefully, if the a value, if the coefficient of that even exponent is positive, then I see that both ends of the tail go up. If the coefficient is negative, that just shows me that the tails both go down. Think about this. If the coefficient is negative, that just means that I've taken my original graph and I've reflected it over the x-axis. Now let's look at the odd function. Y equals a, x to the odd. Looking at the graphs of odd functions, I notice that the tails go in opposite directions. When a is a positive coefficient, I start in the bottom left-hand side of my graph and go in the top right. When a is a negative coefficient, I'm starting in the top left and going to the bottom right. Again, notice that when a is a negative value or a negative coefficient of x to the power, then all I'm really doing is reflecting my first graph over the x-axis to get the same shape, just in the opposite direction. So now I'm going from top left to bottom right when a is negative. So these important characteristics are going to help us throughout this whole unit as we start to analyze polynomial functions. So please go over your notes and make sure that tomorrow in class you're ready to talk about and do some work with these power functions that you were introduced to tonight. Have a great night and see you next time.